let's get started for today. Can you hear me in the back? Yes? Great, thank you. I've been told that there are no announcements I need to make, that they'll all be on Piazza either shortly or maybe they already are up there. But you can go check Piazza after this lecture for all the announcements. Okay, so today's lecture is about classification. So far we've talked a lot about regression, where you're trying to predict some real valued outputs, targets, y, right? Given some set of input features, x. And in particular, we've talked a lot about linear regression, where essentially we're trying to model the relationship between input and output as some linear function. And that's cool and all, but that's not all there is to machine learning, right? In fact, that's a pretty small piece of machine learning. And a lot of you have probably already seen linear regression in some form or another, so you might be wondering, where's the new content? Well, today marks our transition into classification, which is a different set of problems, right? So remember in lecture 1, we talked about regression versus classification, with these two different illustrations, right? Regressions on the left, where we have these real valued outputs that we're trying to predict, and then classification looks something more like, you have each input belonging to a particular class, a particular label, and then you're trying to essentially separate these different classes, right? So that you can predict classes for new data points that you're given. And this will make up the bulk of the rest of the course. We're going to focus mostly on classification for the rest of the course. And it also makes up the bulk of machine learning as people usually think about it, especially in industry and things like that. So what we're going to do today is we're going to come up with a probabilistic model for classification. So remember, what did we talk about when we had our probabilistic model for linear regression? Well, we said that maybe instead of just trying to predict the output, we're going to try to predict a distribution over our outputs, right? So we had something like the output distribution, y given x, right, is some Gaussian, where the mean is a linear function, but then I also have some variance, some sigma squared, that I attach to all of my predictions. Right, so this is my probabilistic model for regression. We're going to come up with a probabilistic model for classification, and in some ways it's going to be even simpler, because we don't even have to think about things like Gaussians and things like that, because discrete labels makes it easier to think about just probability masses rather than probability densities. And then we're also going to see how we can come at the same problem of trying to come up with a probabilistic model from a different perspective, which we call the generative perspective, which hopefully will make a lot more sense later as in terms of what this actually means. And it's going to draw on the knowledge that we've already built up about multivariate Gaussians in order to try to come up with that probabilistic model. And maybe this doesn't make a whole lot of sense yet, but hopefully by the end of the lecture, it'll mean something. So let's get started with our problem setup. Okay, so what does classification actually look like? Well, just like what we had in regression, right, this is still like a supervised problem. So what we're given, right, is a data set, right, of n data points. And each one of these data points is an input-output pair, right? So for each one of these x's that I'm given, the inputs, I'm given the corresponding y, the output, which is the thing that I'm trying to predict. It looks just like regression, right? So then what's the difference? Well, the main difference is that now each y that I have, each output, is something that's discrete, right? So before the y's were real values, right? Now each y can only take on one of k different values, okay? So we'll call these values 0 through k minus 1, because we like zero indexing things in computer science, right? So we're going to call each one of these values 0 through k minus 1. Those are the only k values that y is allowed to take on, okay? It's not allowed to take on any real value. It's just one of these discrete labels. So that's the difference. That's the main difference, right, between regression and classification, is that the y's have changed in this way. So our goal is still to learn a model, right, that predicts outputs given inputs, right? We're still trying to learn this f, right, which has parameters theta, that when given an x predicts a y, right? We're still trying to do the same thing that we were trying to do before. But it's a little bit different now, right? Because now our f of x isn't trying to predict some real value. It's not just spitting out any number, right? It's trying to predict one of these k values, right, between 0 and k minus 1. So we're going to have to figure out exactly how it is that we're going to parameterize our model, how we're going to build our model in order to accomplish this. So just like before, we're going to work mostly from the perspective of probabilistic models. We're going to bring back our old friends, things like MLE and map estimation. We're going to talk about all of those things in the context of classification, right? It's going to give us a unified framework to talk about all of these things. So then we have to actually define what our probabilistic model looks like here, right? So that's what we're going to do over the next couple slides. And we're going to do so from the perspective primarily of binary classification. Okay, what is binary classification? It means that k equals 2. Okay, it means that there are only two classes that I'm trying to distinguish between 0 and 1. So in this picture here, this picture is binary classification, right? Because I only have my green circles and my red x's. There's no, blue triangle. There's nothing else, right? So we're going to focus on binary classification because it's going to be a little bit easier to, formalize things when there's only two classes. Just know that basically everything that I say is readily generalized to the case where k is greater than 2. Okay, it's not super complicated. It's just a little bit easier to explain in this case. So let's actually come up with this. So what's a probabilistic model for binary classification actually look like? Well, in binary classification, right, all of our labels are either 0 or 1. That's where we're starting from, and that's going to make things a little bit simpler, right? So what we're trying to do is we're trying to build a model, right, that goes from x to one of these predictions. It either outputs a 0 or a 1, or more generally, a probabilistic model is going to output a distribution over 0 and 1, okay? Let's think about our linear model from before. So what was our linear model, right? It was something that looked like theta transpose x, right? The problem with something like this, right, theta transpose x is some unconstrained real number, right? This is not something that's going to readily translate into the probabilities that we want. And it also doesn't neatly map onto just 0 or 1, right? So because it's an unconstrained real number, we have to do something with theta transpose x in order to make it the model that we actually want. So it's not quite as simple as regression, right, where we have a real value target, so we output a real number. It's a little bit more complicated than that. We have either 0 or 1 as our target, and so we're going to have to figure out how to take our output and map it onto that space. Well, one thing that we might be able to do, right, is we might be able to take this output, theta transpose x, and have it represent some kind of probability, right? So remember, we're talking about probabilistic models, right? Well, how do we actually make our model output define a probability distribution over y? Well, what do we need for that? Well, y is either 0 or 1, right? So what do I need? I need two numbers, right, that are between 0 and 1 and sum to 1, right? That's how I'm going to represent the probability of 0 and the probability of 1. So that's what I want my output to be, is it's going to be a probability distribution over 0 and 1. However, the only thing I have right now is a real number. So what do I do with that? Well, how about first let's just focus on outputting the probability that y equals 1 given x, okay? So we're just going to focus on outputting that probability. And I claim that for binary classification, this is sufficient. Okay, I don't actually need to represent the other probability. Why is that? Sorry? Exactly, right? So we know the probability of y equals 0 is going to be just 1 minus that, right? So if I just output the probability that y equals 1, I already know what the probability of y equals 0 is. And so what I claim is that it's enough for my model to output a single probability, and then we'll know the other probability automatically. But we're still not quite there yet, right? Because our model is currently theta transpose x, which is a real number. That's not a probability, right? And what we need is a probability between 0 and 1. So how do we make our model output a number that's actually between 0 and 1? I claim that if we do this, then we're done. Okay, why are we done? Because then we can say that what the model is outputting is probability of y equals 1, and then we just subtract that from 1 to get the other probability. And that's what our model is going to be. But we have one step remaining, right? We have our model, theta transpose x. It outputs a real number. And we somehow want to take that real number and convert it into a probability, into something between 0 and 1. Okay, that's the work that we have remaining. So it turns out there's actually a lot of ways to take a real number and then turn it into a probability. But I'm going to tell you about the most common way, at least the most common way that's used in machine learning. It's something called the logistic function. Okay, so to recap, theta transpose x, that's our model. It's an arbitrary number, and we want to turn it into a probability. And the most common way to do this is using the logistic function. Some people also call it sigmoid, xbit. There are different names for this function. All of these names actually mean something sort of slightly different, but at least in the context of machine learning, they're usually taken to mean the following. The sigmoid function is this function right here, okay, and it looks a little bit nasty, but it's actually not super complicated. It looks like this, okay? So the x-axis, right, this horizontal axis is what you pass into sigmoid, that's the input, and then the y-axis, the vertical axis, is what sigmoid is outputting, okay? So you can see it's basically doing exactly what we want it to do. It's taking a real number, let's say like theta transpose x, for example. It's taking a real number and it's squashing it to the range 0, 1. And so that's how we take a real number and then we turn it into a probability. So if we take a look at the horizontal axis, what's happening, right? Well, if the number that I pass in to the sigmoid function is really, really negative, okay, then what happens is that sigmoid outputs a number that's very close to 0, okay? On the other hand, if I pass in a number that's really, really positive, then sigmoid outputs a number that's really close to 1, okay? So that's how I represent something that's really not likely versus something that's really likely, right? The thing that gets passed into sigmoid should be really negative or really positive, respectively. If I pass in something that's close to 0 as the input, then the sigmoid is going to output something that's close to 1/2, which basically says, you know, maybe this could happen, maybe this wouldn't. And so that's what the domain of sigmoid represents, right? The range of all real values, and then really negative is, you know, very unlikely, and really positive is really likely. And then 0 is, you know, 50-50. So this is what our model is going to be. It's quite simple, right? All we're going to say is that the probability that y is equal to 1 given x, I'm going to represent that as a sigmoid transformation of my model output. Okay, so my model output, right, f theta of x, for a linear model, right, that's just like theta transpose x. That's all it's doing. Outputting a real number, that's theta transpose x, and then I just pass that through a sigmoid, and I say that's my probability. So that's my whole model, right, linear plus sigmoid. And that gives me the probability y equals 1 given x, and then I can infer that the probability of y equals 0 is just 1 minus that. Okay, and that's my entire distribution over my label space, y given x, for, you know, this binary classification problem. Yes?
So can you compare sigmoids from different data sets, or
Can you compare sigmoids across different data sets? So sigmoid as a function, right? It's the same regardless of the data set, right? It's just this mathematical function right here. Your model, like say for example theta transpose x, your model might learn to output different values, right? Theta transpose x, depending on the data set that it was trained on, and then that would result in different sigmoid values as well. I'm not sure if that answers your question, though. Okay, yeah, we can also talk more about it offline, yeah. Other questions? So far, so good? Okay, well, if that wasn't confusing, then let's do the MLE of theta. Okay, so this is going to follow a pretty similar formula to what we've done before. Hopefully everybody's seen maximum likelihood estimation enough times that it's starting to get drilled into your brain, right? But we're going to see exactly how it plays out algebraically when we have this particular model, right, in the context of binary classification. Okay, so we're given this data set, right, xi, yi from I equals 1 to n, and we know that each label is either a 0 or a 1. It can only take on those two values, right? And we defined our probabilistic model from before. It's the sigmoid of a linear function, right? That's how we defined our model, or at least that's the probability that y equals 1, right? And then we know 1 minus that is probability y equals 0. So let's actually write out some things. And I hope that this doesn't bug out on me again. I think I figured it out, but I'm not totally sure. So remember, MLE is just the argmax over my parameters. I'm going to start from the non-log version just to make things super clear. right? This is what we had before, right? We're just maximizing with respect to the parameters the product of all the probabilities of all my data points, right? The likelihood. So then the key question here kind of becomes like, well, what actually is this thing right here? What is p theta of yi given xi? Well, we know that yi is either 0 or 1, right? So we want to say if yi is 0, right, then I want to look at p theta of 0 given xi, which is 1 minus my model output, right? And if yi is 1, right, then I would just want to look at, you know, the sigmoid of my model output is 1. It's just p theta of 1 given x, right? And so I claim that the way that you can write this mathematically, this might look kind of familiar if you've you know, ever looked at the, you know, intricacies of something like a Bernoulli distribution or something like that. But even if you haven't, it's okay. We'll go through it slowly, right? It looks something like this, where I have, you know, this product I equals 1 to n of p theta 0 given xi. What is this thing? Well, it's, you know, 1 minus the sigmoid of my model output, right, to the power of 1 minus yi, and then p theta 1 given xi, which is just the sigmoid of my model output, right, to the power of yi. Okay, hopefully this looks familiar to some of you. If it doesn't look familiar to you, let's think about it for a second. Why does this make sense? Well, there's only two cases that we actually have to think about, right? yi is either 0 or 1. Okay, there's nothing else that yi could be, so we only have to analyze those two cases. What happens if yi equals 0? If yi equals 0, then this is something to the 0th power, which is what? 1, right? So I'm multiplying 1 by something, and that something is p theta of 0 given xi, right, to the 1 minus 0th power. So it's just this thing right here, right? And if yi equals 0, then this is exactly the term that I'm trying to evaluate, right? What happens if yi equals 1? If yi equals 1, then this thing becomes 0, which means that this whole thing right here becomes 1, because it's something to the 0th power, which means that I'm just evaluating this thing right here, which is p theta of 1 given xi to the 1th power, right? And so if yi equals 0, regardless of whether yi equals 0 or 1, I get the correct term out that I'm looking for, right? It's either p theta of 0 given x or p theta of 1 given x, and that depends on the y that I'm given. Okay, so that's why we can write it in this way, right? You might be asking, why are we going to write it in this way? Well, actually, it turns out it becomes a little bit easier to sort of analyze once we write it out. And you can probably guess the thing that we're going to do next. The thing that we're going to do next is we're going to take the log, right? And we're going to try to look at the max of the log likelihood instead of the likelihood itself. So if I take the log of this whole thing, well, that's actually kind of nice, right? Because these exponents turn into, you know, coefficients. So it looks something like the following. My product also turns into a sum, right? That's not a very pretty sum, but that's okay. 1 minus yi, right, of the log probability of 0 given xi, right, plus yi times the log probability of 1 given xi. Okay, so that's cool, right? There's a little bit more that we can do to write this out, right? And it involves looking at this term right here, okay? So remember, what is p of 1 given xi? P of 1 given xi is a sigmoid of theta transpose x, right? That's what we're doing to define that term right there. So remember, sigmoid, well, actually, I didn't write it on this slide, but hopefully people wrote it down, or, you know, you can look at your notes, right? Sigmoid is e to the z, where z is your input, divided by e to the z plus 1. Okay, so if I take the log of that thing, well, then the fraction turns into two different terms with the subtraction in the middle, right? And so I get something that looks a little bit more like this, where log of this thing is actually, well, log of e to the theta transpose x, right? So those things cancel, so I just get theta transpose xi, right? Minus log of the denominator, right? And the log of the denominator is this thing. Let me put a bracket around here. So that becomes that term, okay? And then we know also that this term right here is just 1 minus the sigmoid of the model output, right? Well, what's 1 minus e to the z divided by e to the z plus 1? It's 1 over e to the z plus 1, right? So then this thing ends up looking just like negative log of the exponent of theta transpose xi plus 1. So then that's how this MLE starts shaping up, okay? Now, there's quite a bit more, like a couple more slides that we would need to do in order to actually work out what it is that we're going to do with this thing, how are we going to solve it, et cetera, et cetera. But that's actually on your discussion worksheet. So here's the first few steps of the setup, and then you can go to discussion or check out the worksheet on your own in order to see how this actually plays out into a full solution. I might also be doing it next time in lecture. I do not remember. But this is how it starts. Yes? Yeah, sounds good. So let me actually just write this out. I think that'll make it more clear. So what is P of 1 given xi? Well, that thing we said was sigmoid of our model, right, which we're assuming is linear, right? So that's theta transpose xi here, right, which is equal to the exponent of theta transpose xi divided by the exponent plus 1. Okay, so then if I take the log of this thing right here, right, it becomes log of numerator minus log of denominator, right? So then I get log of this thing, which is actually just the thing on the inside. This should be a brace, right? So I get log of this thing, which is just this thing, right, minus the log of this thing right here. And that's the whole term that we have written out over here. Mm-hmm. And this is to be continued, I think in both lecture and discussion. Yes? How does it differ from Uh-huh. There's no theta transpose xi on that side, right? Is that, sorry, was that the question? Yep. Okay, cool. So this classification setup that I've described just now is called logistic regression. I know that's confusing. It's called regression, right? And from a very kind of like esoteric statistical perspective, it is a method for regression, is what statisticians would call it. But in machine learning, we use it for classification. Okay, we're trying to estimate the probabilities that this particular data point belongs to these different classes. Classification problem. But it's called logistic regression. That's just what everybody calls it. Okay, what do I mean by this classification setup? Well, I mean, we take our linear model, right, and we pass that through a sigmoid. That gives us P of y equals 1, which defines for us P of y equals 0. And then, if we're looking at the MLE of this whole thing, all of that encompasses what we call logistic regression as a classification problem, as a classification setup. Okay? You're going to see this more next time, as well as in discussion. But there's kind of a little problem here, which is that unlike linear regression, there's no analytical closed form solution. So there's no like set the gradient equal to 0 kind of solution, and then out pops the best theta. Okay? So remember, what was that in linear regression? It was like x transpose x inverse x transpose y. Just read it off the page. That's the solution that you want, right? Unfortunately here, for logistic regression, as well as in most problems that you'll deal with in the real world, there's just no analytical solution that we can write down. So instead, we have to rely on what we call iterative optimization, or specifically gradient-based optimization, which is going to be the topic of focus for Friday's lecture. Okay, but just as a sneak peek, that's how we actually solve this particular problem, logistic regression. We will talk more about logistic regression next lecture. So this was also a little bit of a sneak peek of Wednesday, just to get, just to sort of set the stage for what classification looks like, right? But for the rest of today, what we're actually going to do is we're going to try and go back and understand what we've done from a different perspective, what we call the generative perspective. Okay, so what have we done so far? Well, from a certain point of view, what we've done might look kind of weird, right? Because all we did was we said, well, maybe our model should look like this, right? Maybe our model should look linear, right? And then we just pass it through this particular function in order to get, the probability values that we want. But why linear, right? Like, why would linear make sense from the perspective of classification? Why not some other type of model, right? And so what we're going to do is we're going to see from a particular perspective, a particular generative perspective, what the linear model actually corresponds to and what underlying assumptions we might be making when we're actually defining this model. Okay, that's the goal for the remaining 20 minutes. So to do so, we need to step back a little bit and actually talk just very briefly about approaches to classification. There are different approaches to the problem of, find a model that, given an input, predicts a discrete output, That's the problem that we're trying to solve, and there are different ways that we can actually try to solve this problem. In particular, if we're thinking about probabilistic approaches, right, where we build probabilistic models like we just did, there are two main approaches or paradigms, if you will, to these classification problems. The first one is one that we might already be quite familiar with based on all this MLE stuff that we already talked about. It's called the discriminative approach. And what we do here is we directly learn this model that we care about, y given x, right? Input given output. And then we say, well, that maybe there is some p of x, maybe my inputs come from some distribution, but I don't know what it is, and I'm going to assume that my parameters theta have nothing to do with p of x whatsoever. And so, it's going to cancel out of all of my MLE calculations and stuff like that. I'm just not going to worry about it, okay? That's what we did so far with logistic regression, right? We directly modeled p theta of y given x. Specifically, we modeled p theta of y equals 1 given x, right, as a sigmoid of a linear. And then y equals 0 was given to us. But this is the general approach that we took, discriminative. There's another class of approaches that we can take, which is called generative. And in generative, you might be able to infer what the difference is that all of a sudden now we actually do care about p of x. Okay? And specifically in generative classification, what we do is we modeled what we call the class conditional, which is this probabilistic object, p theta of x given y. Okay, what does that say? It basically says, if I know that my data point, right, came from a particular class, green circle versus red X, dog versus cat, whatever, right, then what is the underlying distribution for that class, right? Like what data point am I likely to sample if I'm looking at a green circle or if I'm looking at a red X? And then we also model what we call the class priors, P of y, which basically just tells you how likely these different classes are compared to each other. Maybe it's like 50-50. Maybe the green circles and the red X's are equally likely. Or maybe the red X's come up way more often, so then it's like 10% versus 90% or something like that, right? But what we're doing is we're modeling these distributions, x given y and then y, and then how do we get y given x? We use Bayes' rule, right? Bayes' rule will then tell us what y given x is from these other objects, x given y and y. Okay, so that's the main difference between this discriminative versus generative approach, is do we just model y given x directly and then forget about everything else, or do we model these other things and then use Bayes' rule to figure out what y given x is? In the end, y given x is what we care about, right? Because that's what's going to help us make the classification, but there are different ways that we can get there, at least from a probabilistic perspective. There are also some non-probabilistic approaches, for example, approaches that forgo probability entirely and then just reason about what the decision boundary should be, what should be the separator between the different classes. And we're going to see examples of this, for example, something called support vector machines, which you may have already heard of, later in the semester. But we're not going to focus on that just yet. For the rest of the lecture, let's actually take a look at a pretty simple generative approach to the binary classification problem that we've already been talking about. Okay? And this approach is called linear discriminant analysis. And hopefully, after we work through this approach, we're going to see why and in what cases a linear model might actually make sense. Okay, why are we throwing a linear model at the classification problem? Well, LDA is kind of one way to explain under what circumstances that might be reasonable. And the LDA model looks as follows. So remember, this is going to get a little bit more complicated, right? Because before, we only had to define p theta of y given x. And we were doing so directly, right? What did we say? We said, well, maybe it's like a sigmoid of a linear function. Okay, that's cool, that's simple, but we don't really know when that makes sense, what that corresponds to, et cetera. There's some unanswered questions here, right? Well, in the generative approach, you sort of leave fewer things unspecified, okay? In the generative approach, we're going to say, well, now I have to say, what is p theta of y? I have to say, what is p theta of x given y? Right? There's more distributions that we have to model, which makes things a little bit more complicated, but also makes them more concrete, right? Because we're actually specifying the distributions that we think appropriately model our data. So in LDA specifically, we build the following model. So suppose that my class priors are 0.5 each. That's actually not strictly necessary in LDA. But it's going to make my analysis a little bit simpler. So let's say that both classes are equally likely, okay? And then what we're going to do is we're going to model our class conditionals, x given y, as multivariate Gaussians. Okay, so hopefully it's becoming a little bit more clear why it is that we talked so much about multivariate Gaussians. They actually really do pop up everywhere, right? So if I model my class conditionals as multivariate Gaussians, what that means is I have some p theta of x given the first class, y equals 0, right? And I'm going to say that's some MVG with mean mu 0 and then covariance sigma, right? Because x could be some d-dimensional vector, right? And then similarly, my p theta of x given the second class, y equals 1, is also an MVG, where my mean is mu 1, and then I make the simplifying assumption, right, that it has the same covariance. Okay, so sigma is shared between the two different class conditionals, okay? So I don't have like a sigma 0 and a sigma 1. I have just one sigma that's the same for both of them. I'm basically saying I think that the overall spread of these two classes is roughly similar. That's what I'm saying here, okay? Well, once we build this model, right, then remember what we said is that we're looking for p of y given x, right? And the way that we're going to get p of y given x is using Bayes' rule. So let's actually do that. Let's look at p theta. Oops. Well, I didn't actually lose anything, so that's good. I'm looking for p theta, right, of y equals c, where c can be either 0 or 1, right, given x. And the reason that I'm writing c is because I don't want to write out 0 and 1, right? I'm just going to write it out for c, and then you can fill in the blanks for what it should be. Well, what is this thing? Well, if I use Bayes' rule, right, the first thing that I do is I flip this around. So I'm going to write p theta of x given y equals c. And what's that thing? Well, that thing is an MVG, right, of x, parameterized by my mean, mu c, that's either mu 0 or mu 1, right, and then my covariance sigma, times p of y, right, which in this case happens to be 0.5 for both because I made that assumption, and then divided by p of x, right? That's the denominator in Bayes' rule, right? Well, what's p of x? P of x I can express using the law of total probability, right, as the sum over my two classes of p of x given y times p of y, right? So I can write it in this way. Oh my God, no. P theta y equals c given x mu c sigma times 0.5, right, divided by the sum of, let's call it c prime, okay, not like derivative, just like a different c, right, in my two different classes, 0, 1, this is like a very ugly in symbol. of, p of x given y, mu c prime sigma, times p of c prime, which is 0.5 still, right? And so, thanks to this simplifying assumption that, the two classes are equally likely, I have all these 0.5s that get to cancel out with each other, right? So then all I'm left with is, an MVG probability density over the sum of my two MVGs, okay? So what we want to do, right, is we want to use this distribution, right, p of y given x, in order to actually predict a class, right? I'm given an x, is this a 0 or is this a 1? That's the decision that I have to make. Well, what's a natural way that I can make this decision? I just look at these two values, right, p of y equals 0 given x and p of y equals 1 given x, and I just, based on whichever one is bigger, I pick, that class, right? If y equals 1 is more likely, then I predict 1, otherwise I predict 0, okay? So basically I'm saying that if c equals 1 is more likely, right? That's when I'm going to predict 1, right? Then what has to be true? Well, when is it the case that c equals 1 is more likely? Well, it's when this thing, right, p of y equals 1 given x is larger than p of y equals 0 given x. Okay, that's basically all I'm saying here, right? Well, there's a pretty easy way that I can actually write this, which is I look at the ratio between the two probabilities, okay? So it's p of y equals 1 given x divided by p y equals 0 given x. Why am I looking at the ratios? Well, actually, what's really convenient about the ratios is that this denominator cancels out, right? The denominator is the same for both classes. Therefore, I don't actually even have to worry about it. I'm just looking at a ratio between the numerators. So this thing is the following. It's an MVG, probability density, right, for mu1 over the same thing, but with mu0. And if c equals 1 is more likely, if class 1 is more likely, then this thing has to be greater than, or maybe equal to, but greater than 1, right? That's when I'm going to predict 1, is when this ratio is greater than 1. Otherwise, I'm going to predict 0, okay? Now, you might already be able to guess what I'm going to do next because we do it so often. What I'm going to do next is we're going to take the log of this, okay? And what happens when we take the log of it? Well, this fraction becomes a subtraction, right? It's log of the numerator minus log of the denominator. And then the 1 turns into a 0, right? Because log of 1 is equal to 0, right? And so that's what we're going to start with. So basically what I'm saying is we're predicting 1, y equals 1, when the log of the MVG probability density for class 1 minus the log of the MVG probability density for class 0 is greater than 0. Okay, that comes directly from taking the log on the thing from the previous slide, right? So let's actually work that out a little bit because it's not super complicated. This thing right here, okay, this MVG, right? It's like 1 over, the determinant of 2 pi sigma square root e to the something, right? It's some formula that is fairly simple, right? And then when I take the log of that, then all of the stuff in the front I claim just cancels out, or just disappears. Specifically because my sigmas, right, my covariances are the same. I assume that they were the same between the two classes, right? So I'm gonna get a whole bunch of terms that are the same. Then when I subtract them, they just go away, okay? And if that's not convincing, you can write them out on your own. I'm just not going to write them on the slide because there's not quite enough room. But because the sigmas are the same across the two classes, there are going to be a bunch of terms that actually cancel out. And the only terms that remain are going to be the thing that's inside the exponent. Okay, so it's going to be e to the, this quadratic form, right? -1/2, x minus mu1 sigma inverse, x minus mu1, and then the same thing for mu0, right? And so what I'm going to get is something that looks like this. Negative
x minus mu1 transpose sigma inverse x minus mu1, okay, plus x minus mu0 transpose sigma inverse x minus mu0 is greater than 0. Okay, that's just writing out this thing that I already had. Okay, you notice that I also got rid of some 1/2. That's because I can just multiply by 2, and then those go away. That's easy enough, right? Well, what can I do here? Well, actually, one thing I can do here is I can, essentially use the multivariate version of FOIL, right, and then start writing out what these quadratic terms actually look like. That'll give me a little bit more insight into how to analyze this thing. Okay, so I can write it like this. I can write negative x transpose sigma inverse x, okay, plus 2 mu1 transpose sigma inverse x minus mu1 transpose sigma inverse mu1. Okay, so this thing that I've written so far, right, that's just this first term expanded, right? It's a useful exercise to be able to do this on your own, to go from here, right, to this expanded form here. And then I can do a very similar thing for the second class, right, which is, plus x transpose sigma inverse x minus 2 mu0 transpose sigma inverse x. I'm running out of space, so I'm going to write on the next line, plus mu0 transpose sigma inverse mu0 is greater than or equal to 0, or maybe just greater than 0. Okay, well, there's one thing here, which is that this term cancels out with this term, right? X transpose sigma inverse x, those two canceled out, right? Which is nice because that was actually the only quadratic term that I had, right? That was the only term that was quadratic in x. Everything that I have left is actually just linear in x or doesn't involve x at all. Therefore, I claim that we could write this whole thing in the form w transpose x plus b is greater than 0. Okay, what is w? W is sigma inverse mu1 minus mu0. B is a little bit more involved, but it's not that complicated. It's 1/2 mu0 transpose sigma inverse mu0 minus mu1 transpose sigma inverse mu1. Okay, well, those particular values for W and B might not be super meaningful. You can squeeze out a little bit of meaning if you stare at them hard enough, but that's not really the main point here. The main point here is that our decision rule, right, our thing that goes from inputs to predictions is linear, right? We took our input and we transformed it with a linear function, and then we're just asking, is this greater than or equal to 0? If so, predict class 1, otherwise predict class 0. Okay, how did we get this? Well, we made some particular assumptions, right? We made our assumptions that the class conditionals x given y are these multivariate Gaussian thingies, right? We also made our assumption that the covariance matrices between these two classes were the same, and that's how we got the quadratic terms to disappear, right? So if you think, for example, that you're working on a problem where the class conditionals actually do kind of look like MVGs, right? And you think that they kind of look similar in the sense that they have similar covariances, then it's pretty reasonable to apply something like LDA and then get out a very simple linear decision rule, right? Essentially a linear model for how you're classifying between these two classes, okay? So when we were asking before, like logistic regression seemed like kind of this arbitrary choice, right? Like why are we specifying a linear model? Well, the reason is that in certain cases, right, we can make these modeling assumptions that actually make the linear model make sense, okay? It's kind of nice that for logistic regression, we don't have to make those specifications. We can just say, well, let's just try a linear model, see what happens. But it's also nice to be able to understand when and why that might actually work and why we might do that in the first place, okay? So this is kind of the discriminative versus the generative approach. In the discriminative approach, I start from my model. I say, here's the model I want to build. Let's hope that it works out, right? And in the generative approach, I say, well, here's what I think my data looks like, right? And if my data looks like this, then what's the decision rule? What's the actual model that I get out? Okay, so that's the two different ways that we can sort of approach these different problems. And sometimes they have, these relationships like logistic regression can be motivated from this perspective of LDA and the model that it actually builds. Yes? Fantastic question. So is one approach more accurate than the other? In the next slide, I'll talk a little bit about how to compare and contrast between generative versus discriminative. Yeah. Yes. How did I get from here to here? Yeah, so this thing, right, is, all right, test me. Let's see if I can write this out on the spot. Oops. This thing, right, is like 1 over, I think, this. I think. So if I take the log of this thing, it's log of this, right? But the thing is, I'm going to get a log of this from both this thing and this thing because the sigmas are the same. So then because I'm subtracting, those go away. I just didn't write those down at all, right? Plus log of this thing, but log to the e of something is just the thing on the inside. So then that's the only thing that I actually ended up writing. I also multiplied everything by 2. Okay, so then let's finish up by actually talking about, actually I have 2 more slides. Okay, so there are a number of modifications that we can make to this LDA model that might make it more complicated or more simple, but maybe a better fit for different problems that you're working on, right? So for example, what if we have sigma 0 and sigma 1, these different covariances, and they don't actually correspond to each other? Then we get a class of methods called quadratic discriminant analysis, which is more complicated because now your classification rule is quadratic instead of linear in X, but it might be a better fit if you think that you have different classes modeled by different covariances. Or what if I have underlying class priors that are not the same? So one class is more likely than the other. This actually results in a very simple change to the classification rule. It's still linear. You just have an extra term thrown in there. And I'll leave this as an exercise because it's actually kind of interesting. Lastly, what if we can assume that we have diagonal covariances? So like, these different features of my input don't actually even correlate with each other. They actually just correspond to, independent, so like diagonal covariances, there's only variances, right? This is an assumption or a model that people call naive Bayes. Naive because it's a rather naive assumption, and Bayes because remember we're using Bayes' rule to calculate the final predictions that we want to make, right? And this classification rule becomes even simpler to compute. You can essentially think of each feature dimension as being independent and then, working with it separately. But again, not something that we're going to cover in the interest of time. What I want to do is to conclude by talking a little bit about generative versus discriminative classification at a high level, which I think is a question that we had earlier. Generative classifiers do have some advantages. For example, they have an explicit notion of p theta of x. Right? We're actually able to say, given an input, how likely do I think this input is, right? If I'm modeling my classes as, class conditionals as Gaussians, and then I get a point that's all the way out here, right? My generative model can say, well, that's an unlikely input. Whereas my discriminative model has no idea what's likely versus not likely for the inputs that it's given. And so this might be useful for doing things like detecting outliers, right? Or finding out that there are anomalies in your data. And sometimes they can also be more effective when you have limited training data. So sometimes if my n is small, then the generative model can train better, can learn a better model, more effective model than the discriminative model. Nevertheless, discriminative classifiers are very much the standard way to go simply because they work better. People have found more effective techniques for learning discriminative models, and that's pretty much what everybody does in practice, especially with something called neural networks, which we'll talk about next week. The last point is that if we're working with complex inputs, like for example images or something like that, then modeling these class conditionals become really hard, right? It's no longer just like some MVG that we're throwing at the problem. And that's the main bottleneck behind why generative models are very hard to learn. It's very useful to understand this perspective, but in practice, we're going to be going with discriminative models most of the time. OK, so I'll stop here, and I'll have office hours now if anybody has any more questions. Thank you.